Large language models have been shown to work extremely well on full-stack software projects, especially in ecosystems like TypeScript and Python, where patterns are well established and feedback is immediate. What hasn't been tested to the same extent is how these systems perform in more unforgiving domains like scientific computing or high-performance numerical code, where small mistakes don't fail loudly, but they fail silently. In this video, I want to test exactly that, how well an agentic coding system performs when asked to solve a physics problem using code. We'll use the two-dimensional heat equation as our test case. It's a simple diffusion equation, but it's surprisingly good as a benchmark because getting it right requires reasoning about numerical stability, about boundary conditions, and also requires validation with an analytical solution because we have one for the 2D heat equation. How I'll be benchmarking this agentic coding system, so I'll specifically be using Claude Code for this problem, is by clearly defining the physical problem and the constraints of the problem, much like an engineer would be working with an intern, for instance, but I won't be solving the problem for it entirely. The numerical decisions are going to be made by the LLM. At the end, we'll look and evaluate the result the same way we would any scientific code by checking the mathematics, that the assumptions are true, and we'll see how the solver behaves when we deliberately push it past its stable regime, so to say. So without any further ado, let's hop into Claude, which you can see here, and we'll start off by creating a project for this, and we'll start Claude in this directory here. So how I usually start off any of the projects with Claude is by first just talking to the LLM, trying to figure out a good starting point, explaining to it the questions which I have, and essentially building up some useful context before we set up our different Claude MD and agent files, sub-agents and skills if we need it. So I'm going to be prompting it to essentially write C++ code to simulate the 2D heat equation given some input parameters. We'll go into plan mode for this. So let me just talk about this. In this project, I want to implement a C++ numerical solver to solve the 2D heat equation and visually compare the results with analytical solutions. Please help me structure the problem better by asking me questions and come up with the ideal set of agents, skills, and MCP servers, along with the Claude MD for this project. So we're going to run this and see how it decides to initialize this project. Great, so we've got the first set of questions which it's asking us. To keep this simple, so to use a finite difference numerical method, matplotlib to keep things simple for this. Conditions do you want to support? All of the above to see how well it does on its own. And for the build system, we're going to use minimal external dependencies. We don't want to go into Eigen or any of the parallel computing frameworks for now, but this would be interesting to look at how it deals with that in the future. But for now, CMake and minimal dependencies, and we're going to submit those answers there. So what I expect it to do here is tell me what the ideal agents or the skills or MCP servers that I need to use are before I get this project started, and Okay, so it's asking me a few more questions here. So it's picked up on the CFL condition for the explicit forward time central space. We're going to go ahead with the simple but has stability constraints. Analytical solution do you want to compare with? We are going to compare it with separation of variables, and we're not going to worry about parallelization for now. The purpose of this is, I think we're going to look at this as a balance between learning and demonstrating competency. Okay, it has made its comprehensive plan, and it's asking me a few final questions to ensure that the plan fits what we expect. Do you want to set up the custom Claude skills / commands like build, test, visualize as part of this implementation? And we're going to go ahead and say yes, so we can repeat these 3 steps easily going forward instead of having to make this or rewrite the same prompt over and over. Main and grid resolution you want to use as defaults. To stick to a unit square for the purpose of this test, which is quite common in textbooks. And would you like to handle the initial conditions? How would you like to handle the initial conditions for analytical comparison? I'm going to start with a Gaussian bump, a bit more interesting results. So Claude has noticed something here, 2 answers. So it rightly noticed that separation of variables for the analytical solutions, but the Gaussian bump as the initial conditions is going to be a problem in the analytical solution where variables you'd ideally want to have a sign as the initial condition. So how we're going to deal with this here is use a heap kernel for the Gaussian initial condition. That it's more advanced maths, which is true, but it will give us better or more interesting results to compare. So we're going to go ahead and change this. So this is quite good that it's able to pick this up. And great, this looks like the end of the planning phase. Just go up and look at the output which Claude has given. The project summary, a C++ numerical solver for the 2D heat equation using the explicit forward time central space finite difference method with Python visualization for comparing numerical results against analytical solution. This is a course project focusing on clarity and demonstration. It's irrelevant here, but you can see that it's come up with a project. So looking at it straight away, we see that it's got the Claude MD file and the README for the project documentation, and to decide to split up the source into different modular parts. So we have the solver, which actually implements our finite numerical solver. We have a different interface for the boundary conditions and how they're handled with each one of the 3 boundary conditions, the Dirichlet von Neumann and the periodic boundary conditions, and it was able to abstract away the grid as well in the engine and also abstract away the initial conditions. And here we have the data exporter, which we assume will be used for the Python visualization. So this is quite impressive that it's able to come up with all of this on its own, but this is something we'd expect. Now see how it's able to implement each one of these. We're going to first check if it's able to one-shot this problem, and I won't be prompting it at all to start off with, so I'm just going to go ahead and press auto accept edits. Okay, so something very interesting. We've got a recommendation for the LSP server for C++, which was only added 1 day ago, and I'd be quite interested to see how well this performs. So I'm going to go ahead and install the LSP server. Great, we've just passed the 10-minute mark here in Claude, and it's just come to the end of most of the source code implementation. It's asking me about creating the build MD, which I presume is the slash command for, which I presume is a slash command for the build. One thing I did notice before going into more details is that you can't see here because it's lost a lot of the history, but what it ended up doing was creating all of the source files before actually running the skill creation or the slash command creation. So it wasn't incrementally testing and building for each additional feature. It, in a sense, what I asked it to do, just one-shot the whole problem, implemented all the headers, all the source files, and also completed implementing all the Python comparison files before it even got to any of the building or the testing phase, which can be quite problematic once you're working with lots of different parts of a system interacting with each other. It would be interesting to see how we can steer Claude with just a minimal amount of information to make sure that it splits these phases properly and is testing at the end of each phase, which would ideally just be another command in the Claude MD file. But 66k tokens that have been used up in the context, which if you go back a month or so, we would have had much more context used up, but recently some changes to compaction and summarization, which has made Claude a lot more efficient. Yep, so we see now the phase of going back and iterating the build errors, which can be much more cumbersome if you have a big set of source files, but it looks like the build is successful now. This is an interesting remark here. One test failed due to the steady state not being reached. I wonder how it made this inference. This is something we can go into, so if we press Control O, we should see the whole history here. Oh, showing detailed transcript. There seems to be a bug here, so I'll go back. We've increased the time horizon to test if steady state has been reached, and now it looks like all the tests are passing. Now we are going to essentially run the solver, so run the heat equation solver with 51 cells in the X direction, 51 cells in the Y direction, and save this for checking with the analytical solution. Great, okay, so it's like it has written all of the code which we originally asked it to, built and ran test suite for this. Now, this is what we expect Claude to do, but it was able to work autonomously for about 15 minutes with very minimal input from my end. Now we can go ahead and check if these results are actually in some way consistent to the analytical solution. Again, Claude prompting us what we want to do next, visualize the results. We do have a slash command for this, which can be done, but let's go ahead here. So it hasn't tested if the Python works, so it has essentially concluded the project as finished, but yeah, we need to be able to set up our virtual environment with required packaging and so on. So we'll let Claude install the virtual environment and set up these packages for us. Okay, now running the visualization script, and we see here that some plots are saved. We have some error metrics here, and Claude is actually analyzing the images by itself. So we have a comparison of the solution at different time steps, and then a plot to compare the results. We can also create an animation, but before we do that, I'd be very interested to see how these plots actually look. So we're going to go ahead and take a look at these plots now. Okay, perfect. We have the results here. So straight off the bat, I have to say that this was more than I expected. I expected a comparison between the analytical solution here and the numerical solution. We see that at the initial time is very little difference between the two. There's some numerical errors on the boundaries, and we have the temperature cross-section at 0.5, and they match almost identically as you'd expect at the first time step. But again, this is a lot more information that I would have expected, so this is really good. Now on to the second plot we have. So if we just go on to this, we see here what we notice is that there is some error which is accumulating. So this is a T0.45. Again, we look at the actual temperature at a cross section, the solutions match almost identically. And if we look at the errors in this region, it's of the power 10 power minus 3, where we're looking at the absolute values of the order 10 power minus 1. So yeah, almost 1% average accuracy in this region, which is really good for the numerical solution compared to analytical solution. And if we go on to the next time step, we have again a bit more error which is being propagated around the boundaries, but we really look at this as a percentage error comparison and the solution at a single y cross section. We see that yeah, it's good. We see that the numerical solution matches very well with the analytical solution here. So this is in a way exactly what I'd expect to see in a problem like this, and it was able to automatically come up with how to visually represent errors, show the L2 error, the L2 error, and so on. So yeah, really with how much it was able to achieve by itself. There was also an option to animate these errors, so let's go ahead and quickly see what that is. Before we do that, actually, we have another plot here which Claude has generated. So the error evolution. So what we see here is it starts off with very low error, and as we'd expect, the values propagate up until as we go further forward in the time stepping, and it seems to be going down here, which I guess is when the system reaches steady state and the errors stop accumulating. So this is the type of behavior we'd expect from the numerical solver. So this is great to see this. And just from a UI perspective, let's animate these solutions and see what Claude has come up with. Okay, so we have the actual GIF of the comparison animation. What we see here for the first time is that the error of the error seems to be off, and now we can't actually see the effective magnitude of the error between the numerical and the analytical solutions, which is not very helpful. So I think that's the first thing which Claude wasn't able to do well. Ideally, we want the scale on the error to be of a different order of magnitude and scaled properly, so we see the difference like we did in the previous plots, but wasn't able to capture that well in this example. But again, we see from this that the numerical solution matches the analytical very well, and it's able to simulate those dynamics. And we have a second plot here of the solution at the bottom. So yep, wasn't expecting it to be able to one-shot this problem, but it seems to have done incredibly well on that sense. What we need to see is how it would be able to do when you have more moving components in the solver, because again, as I mentioned earlier on, it didn't build incrementally and it didn't start testing incrementally. So once you have more parts working together, how is that going to affect the process of Claude, and will that cause more errors? That's something we need to look into. Another thing is, did it have good enough multimodal capabilities for the GIFs in order to come up with errors which are scaled better? I think that would be another aspect which we need to look further into. And we haven't really dug into the code too much in this example. We've seen a high level overview that each different part of the solver has been put its own modular with the interfaces. But the code grows, how well does Claude manage these sections? I'd be quite keen to look at that coming up in the future as well. But on this specific task of the 2D heat equation, it was able to do really well. It was able to figure out the CFL condition, implement different boundary conditions as well, which I looked at for the plots, and the results look very similar to this. And yeah, well, took about 20 minutes, and 90k of the context window was used for this. So great. The next step, I'll be looking at trying to build a more complex PDE solver. Maybe we look into implementing OpenMP or other paradigms, see how Claude does when there may not be as much documentation, and how we can give it information about the latest set of documentations for evolving in C++, for instance. But yep, I hope this was useful, and if you'd be interested to see more of this kind of analysis, please subscribe, and yep.